So we're going to look at this sum to infinity, also called the limiting sum. Now just a note, we only look for sum to infinities if we know our ratio is in between -1 and 1. Now if our ratio is in fact in between -1 and 1, if you think of your exponential curve, now because the base is a fraction, it's our backwards exponential. As n approaches infinity, we know that curve's going to 0. So we know as n approaches infinity, r to the power of n will be 0 if our ratio is in between -1 and 1. So what we're basically saying is that sequence will converge to 0. Well, our formula for the sum of n terms was this: a on 1 minus r to the power of n over 1 minus r, but now we're looking at this as n approaches infinity. We know the r to the power of n part is going to approach 0. So therefore that whole formula now just becomes a on 1 minus r. And that's our formula to find the limiting sum, or the sum to infinity. So that's where it comes from. So we get these sorts of questions. We'll be given a pattern and they'll just simply say, well look, does this have a limiting sum? Will it converge? Well, we can look at our ratio here, 4 divided by 56. Well yeah, that's less than 1. So yep, that would have a limiting sum. That's the key piece of information. We want to know whether or not something has a limiting sum. This classic series, a half plus a quarter plus an eighth. It's the old frog in a well question. You know the frog in the well question? You got the frog and can jump half, but each time he can only jump half as much again. Does the frog ever get out of the well? Okay. Well, let's see. He jumps half, then jumps a quarter, then jumps an eighth, keeps doing it. Well, first term is a half, the ratio is a half. Put it into our sum to infinity formula and we get 1. So no, the frog never gets out of the well. It can get to the edge, it can jump the height of the well, but then that's as far as it can go. It's a stupid frog when you think about it. What's it doing? Oh boy, I'm almost out. But I can only jump half as much as... never gets out of the well. Let's go back to this sort of question. Now if we had to write 0.36 repeater as a fraction, well we know what that is. It is of course 36 on 99. So yes, and if they wrote the question like that, that's all I'd do. Oh, that's 36 on 99. But sometimes they might say, by expressing it as an infinite series, in which case I'd rewrite 0.36 repeater as something like this: 0.36 plus 0.0036 plus 0.000036 and so on. And what we've actually created is a geometric pattern. The first term is 0.36, the ratio is 0.01. I could put that into the sum to infinity formula and we get 0.36 over 1 minus 0.01, which does turn out to be the 36 on 99 that we were expecting. That one does simplify down, so it's 4 on 11. So make sure you read the question carefully. As I say, if it just said that, I'd just write the answer down, 36 on 99. But if they had specified by writing it as an infinite sum or something like that, well then, alright, I've got to use this formula to do it. This one comes from last year's HSC. It was an interesting one involving limiting sums. We've got this geometric series that involves algebra, x plus x squared plus x cubed. We're told it does have a limiting sum. So it does have one. I said, look, consider this graph. Y equals -1 minus 1 on x minus 1. But they do say, or otherwise, as they often do in these questions. So it says, look, you don't have to do it the way we're suggesting. If you really want to do it another way, you can. But we're just giving you a big hint here. This is probably the quickest way of doing it. Find the range of values of S. Well, sum to infinity would be A, which is x, on 1 minus R, the ratio is also x. That's how it ties in with the graph. Hopefully people, when they did this in the HSC, realised, oh hang on, I can rewrite this fraction as -1 minus 1 on x minus 1, the expression they gave us. There's the graph. It's our hyperbola being shifted a bit. So what do we know? I want the ratio, which is x in this case, to be between -1 and 1. Now, when x is -1, if I read down on my graph, we can see we get -1/2. So it's saying, what are the possible values of S? We're restricting the domain from -1 to 1. What happens to our range? We can now just look at the graph and go, okay, hang on, when I restrict that domain to -1 and 1, I can see that S is always greater than -1/2. So that's all the possible values of our limiting sum. A nice little question. Okay, shall do us.